Hello everyone, I'm Xing. Today I will present my project on developing a machine learning model that predicts whether a credit card application should be approved. More importantly, this system was designed following responsible AI principle to ensure that predictions are transparent, explainable, and fair across applicants. From a business perspective, such a system can help financial institutions streamline credit approval decisions, reducing manual review workload and improve operational efficiency while maintaining regulatory compliance and customer trust. In this presentation, I will briefly cover three aspects: the modeling, workflow, and performance results, how I evaluated the model fairness, and how I improved model explainability using responsible AI technique. The dataset contains demographic and financial information about credit card applicants, including variables such as income, employment history, family structure, housing type, and occupation. The target variable indicates whether a credit application was improved. One key challenge in the dataset is strong class imbalance. A much larger proportion of applications are rejected compared to approved ones. Because of this imbalance, accuracy alone would be misleading. For example, a model that simply predicts rejected for every applicant could still achieve high accuracy while failing to identify qualified applicants. Therefore, I focus on more informative evaluation metrics including precision, recall, F1 score, and ROC-AUC. During the processing, I handled missing values, encoded categorical variables, scaled numerical features, and performed feature engineering. For example, I created variables such as income ratio and employment related indicators to better capture financial stability. Next, I compared several machine learning models using cross-validation. The model included logistic regression, random forest, light GBM, and XGBoost. The cross-validation results showed that the logistic regression achieved the best balance between recall and F1 score. In constructs, tree-based models tended to predict the majority class due to the strong class imbalance, resulting in very high accuracy but extremely low recall. In the credit approval context, recall is particularly important because missing a qualified applicant represents a lost business opportunity. After further experimentation, I used light GBM with hyperparameter tuning and threshold optimization to improve the final model's performance. Although logistic regression performed the best in cross-validation, light GBM was further optimized through hyperparameter tuning and threshold optimization to improve recall. After training the final model, I evaluated it on test dataset. The model achieved a recall of approximately 0.85, an F1 score of about 0.24, and ROC-AUC around 0.55. Although the overall predictive power was moderate, the high recall indicates that the model successfully identified most potential approved applicants. To better address the class imbalance, I implemented the threshold tuning. Instead of using the default probability threshold of 0.5, I evaluated the model performance across a range of thresholds and selected the one that maximized the F1 score. The optimal threshold was approximately 0.022, which significantly increased recall for minority class. From a business perspective, this approach prioritized identifying potential eligible applicants while allowing additional manual review for borderline cases. In credit approval scenario, false negatives are particularly costly because rejecting qualified applicants may result in lost business opportunity. To further evaluate the model performance, I analyzed the learning curve. The results show that the training performance is much higher than validation performance, indicating some degree of overfitting. However, validation performance stabilizes as the training size increases, suggesting that the model has reached a practical performance limit given the available features and data. A key part of this project is ensuring that the model follows responsible AI principle. Therefore, I conducted a fairness analysis across gender groups. To assess fairness, I compared several metrics between male and female applicants, including the true positive rate, false positive rate, and positive prediction rate. The results showed moderate difference between groups but no extreme disparity, suggesting that the gender alone is not the main driver of model predictions. Nevertheless, fairness monitoring remains important in real-world deployment. To improve transparency, I also implemented model explainability techniques. I use SHAP values to provide a global explanation of the model and identify the most influential factors affecting predictions. These results showed the variables such as income level, employment history, and financial stability indicator play important roles in the model. In addition, I used LIME to generate local explanation for individual predictions. This helped decision makers understand why a specific application was approved or rejected. Explainability is particularly important in financial service, where regulatory requirement and customer trust demand transparent decision making. In conclusion, this project demonstrates how machine learning can support the credit approval decisions while maintaining responsible AI practice. The model can serve as a decision support tool that helps identify potential eligible applicants and reduce menu review workload. At the same time, fairness evaluation and explainability techniques ensure that the system remains transparent, accountable, and aligned with regulatory expectations. In real-world deployment, such a model should assist risk analysts rather than replace human judgment. Future improvement may include incorporating additional financial data, continuously monitoring fairness metric, and retrain the model as new data becomes available. Thank you for your time.